Welcome to this session on Aspen Plus. We'll be continuing from where we left off, and today we'll be treating tubular reactors in Aspen Plus. Last time we looked at a CSTR example, and we solved a problem. Also went through how to specify parameters for a CSTR in Aspen Plus. Today we'll be looking at the tubular reactors, the black flow reactor and the packed bed reactor. And these reactors are also known as differential reactors because of the axial variation in concentration along the length of the reactor. These are design equations as we did for the CSTR. This is the design equation for a packed bed black flow reactor, and the basis is the reactor volume. And this is for the packed bed reactor, which has a basis of a catalyst weight. And you see the similar things that were looked at: the material balance, energy balance, the pressure drop equations. And so we need things required to specify these reactors are similar to that for the CSTR, except the volume of the reactor is specified in terms of the dimensions of a tube. Right, so it's a cylindrical container or a vessel, cylindrical vessel. The pressure of the reactor is also one. We need Arrhenius relations and the rate law, the parameters for the Arrhenius equation, the temperature, and the other process conditions, and depending on the configuration for the reactor. For instance, you may have a multitubular reactor, and that will require specification for the number of tubes. If it's a single reactor, then that also has to be specified. If it's a PBR, packed bed reactor, then we need a weight of catalyst, density, porosity, pressure of the reactor. The rest are similar to the black flow reactor. Right. We're going to repeat the previous example that we solved with the CSTR, and we are going to replace the CSTR with the PFR. So if we go back to that simulation, you can swap the model palette, go to R plug, select R plug, PFR, connect the streams. Since it's the same streams as we used for the previous example, we do not have to do any stream specification. However, we have to convert the volume to the proportional dimensions. Since it's the same 500 liters as we used in the CSTR example, we have to find the dimensions of that reactor volume or reactor size. We have been provided with the length to diameter ratio, and based on that, we're able to estimate the length and the diameter for the reactor. So we quickly into our configuration sheet. So the reactor type, we can decide to run it adiabatically as in the first case. Then we specify the dimensions, the length, and the diameter. Then we've already added the reaction. So we just add the created reaction to our selected reaction sets, and that should be it. You can run the simulation. We do that, view the results. With the results, we're able to see that they tend to have temperature zones or profiles instead of constant temperature across the length of the reactor, along the length of the reactor. And we are running to the vertically. So the temperature drop due to the endothermic nature of the reaction. So we could check that before, and we can see that there is that drop first sharply and then much slower as the concentration of the reactants drop, as they are not high enough. A lot of it has already been consumed. They're approaching the end of the reaction. And if we check our we're to check our conversion by going to the stream results, you can see that about 47% conversion is being attained compared to the 38 obtained for the CSTR. We could also run this reactor isothermally. Come in here and specifying a constant fluid temperature of 1100 Kelvin, the inlet temperature. And we could run that. And you see the amount of heat required, what we have to supply to keep the reactor's temperature at that point, at the feed point. And also we can check to see that we are converting almost everything. It's a 100% conversion. Right. And there are a lot of options available. If we add process streams to this simulation, assuming you wanted to specify your cooling and heating, right? In this case, the heating. If you add those streams, you're able to select one of these options depending on the configuration of your heating or cooling, the countercurrent thermal fluid, and you specify some U, right? Then if the material and temperatures have been defined for this stream, you'll be able to perform the calculation for you. So that should be it for black flow reactors and their simulation options in Aspen Plus. Next, we would look at a packed bed reactor, and we'd see that it doesn't differ much. It's the same block. It doesn't differ much from the PFR minus the specifications. In terms of specification, the presence of a catalyst and the pressure. Right. So we will use this example, attempt solving this problem using Aspen Plus software. Yeah. So we have ethylene oxide is produced by the vapor phase catalytic oxidation of ethylene with air. We have a balanced reaction as shown. It's fed at this temperature, this rate. So a packed bed reactor, a multi-tube packed bed reactor. These are the two dimensions. There's a catalyst packing, right? And the number of tubes per bank, and there are 10 banks, 1,000 tubes. There is a flow rate per tube. We also have the parameters for the catalyst and then the reaction rate parameters. Right. So we specify our components as follows: ethylene, oxygen, nitrogen, and then ethylene oxide. So then we choose a property method. It should be Peng Robinson. Choose that property method and go to the flow sheet. And the feed parameters. So we first find the mole fractions of each of the components in the feed stream. And we should have ethylene there. And we have the ethylene flow rate, which is 136.21. And based on this, we're able to determine the molar flow rates. Based on the feed is stoichiometric. So for every 1 mole of the 0.5 moles of oxygen is fed. And based on that, if we have the ethylene, the fraction of ethylene or the ethylene flow rate divided by ethylene plus oxygen, and this represents nitrogen. That should give us the mole fraction of ethylene in the feed. So we can do the same for oxygen, and then the difference represents nitrogen. And based on that, we're able to estimate the total flow rate of the stream. So that is done here. We have the total pressure as well. So based on that, we're able to specify everything. And then for the material stream, and it's the same block as the PFR. So here we choose to specify the temperature, maintain it at 260 degrees Celsius. Right. Then for the configuration, 1,000 tubes, select multi-tubular reactor, 1,000 tubes, these dimensions, right? And you add the reaction by going to the tab, creating a new reaction, specify the reaction as such, right? Based on our rate law, the exponent of the ethylene in there is one third, and that of oxygen is 2/3. And the coefficient according to the stoichiometry of the reaction is -1 and -0.5 because they are reactants. And we do not have the product in the rate law, so its exponent is 0, and its coefficient in the reaction is 1. It's a product. And when you go to the kinetic parameters, the Arrhenius the temperature dependent K does not have the temperature dependence part in this case. So we specify it as such. This is the pre-exponential factor. And the other parameters go to 0. It's a vapor phase reaction, and it's based on the weight of the catalyst. So you do that selection, and that should be it. So when you come back to your PBR, in the reactions tab, you add it to the reaction set, and removing it there. And then we go to the pressure, the inlet pressure. It's the pressure of the feed material, 10 atmospheres of pressure. The pressure drop in this case was 4.67 atmospheres. And the catalyst weight is 20 kilograms catalyst per tube. So overall 2,000 kilograms of catalyst because there are 1,000 tubes, 20,000, sorry. The bed voidage as we have in the problem. And with that done, you can run the simulation and have your results as shown. So you can go to the results and see the duty, the amount of heat that has to be removed to keep the temperature as specified because of the exothermic nature of the reaction. We can also go to the streams to check the conversion. And you can see this, when done, is about 60% conversion. We can also look at the profiles. You come to profiles here, molar composition. You can customize it and then check for the various components in there based on the length of the reactor. You can see how the concentration of the product rises whilst the reactants falls as expected. We can also look at the pressure drop profile. It's based on the reactor length. And you see it drops linearly till the exit at this point at the end of the reactor. So that is it for the packed bed reactor in Aspen. As I was saying earlier, you could decide to run with the specification of your cooling or heat by adding the utility stream. It's the process stream. So in this case, I could decide to use water. So adding water to my components here, add water, and then come here. If water is my coolant, let's add that stream, the input and output, and specify the parameters for my water. And if I do this, once I do that, I can come here and choose to specify a reactor with any of these configurations, depending on whether the coolant is flowing counter current or cold current, or if it's a constant thermal fluid temperature. The temperature of the fluid does not change. So depending on the configuration you have, you enter the heat transfer coefficient as follows. And when you run the simulation, check the results, you see that the heat duty has dropped. It's been able to remove much of the heat, but I wasn't able to do all. I can increase the flow rate 0.7 and run once more. It's still not enough. If I can, let's see, 1 kilogram, that should probably do it. State, we see that changing that value can affect how much we're able to do. And we can go back to the results and get the plot again. And we see we spoke of a profile for the temperature, and that is what we have. So that does it for reactors in Aspen Plus. Next, we'll be looking at modifying the kinetics. If you have a different kinetics, you don't have a power law model. How do you go about specifying that? So we'll be looking at that in Aspen Plus. Thank you.